Welcome to Session 2.2, The Economics of Custom AI. In our last session, we covered how models learn from the ground up, supervised learning, unsupervised learning, and everything in between. But here's the hard truth of modern enterprise AI. In 2025, we almost never start from zero. Training a foundation model like GPT-3 or Llama 3 from scratch can cost upwards of $50 million and require thousands of GPUs running continuously for months. That's not a project, that's a capital allocation decision for the board. So the real question isn't, can we build our own AI? The question is, how do we take a model that already knows nearly everything and make it an expert in our specific domain, at a cost that makes business sense? That's exactly what this session is about. We're going to move from architecture theory to financial reality. We'll examine every technique on the spectrum, from full fine-tuning all the way down to QLoRA, and we'll put real dollar figures on each one. The subtitle on this slide says it perfectly: Parametric Efficient Fine-Tuning and the Evolution of Enterprise Leverage. By the end of this session, you'll know which lever to pull and how hard for any custom AI initiative your organization faces. Let's get into it. Before we can talk about fine-tuning techniques, we need to establish the foundational concept that makes all of this possible: transfer learning. Look at this slide. On the left, you have a basketball player. On the right, a volleyball player. And the key insight is in those blue arrows connecting them: spatial awareness, core conditioning. These skills transfer directly from one sport to the other. Think about what it means to spend 15 years playing competitive basketball. You've already mastered footwork, hand-eye coordination, reading spatial relationships, and peak cardiovascular stamina. If you decide to pick up volleyball, you aren't starting from zero. You transfer those underlying, universally valuable skills to a new domain. You only need to learn the new game, spiking mechanics, net timing, the specific playbook. The caption at the bottom of this slide captures it precisely. You don't need to rebuild the athlete from scratch. Transfer learning relies on reusing universally useful baseline conditioning to master a highly specific new game. In AI, the same principle applies. A pre-trained foundation model has already spent its childhood processing the entire internet. It already understands grammar, logic, causality, and basic human reasoning. It is our seasoned athlete. We don't need to rebuild that from scratch. We just need to teach it our specific game, whether that's drafting legal contracts, diagnosing medical anomalies, or navigating your company's internal support processes. This is transfer learning, and fine-tuning is how we make the transfer happen. Now let's look at how fine-tuning actually works at an architectural level. This slide gives us the most important mental model of the entire session. Notice the layered structure. At the bottom, you have the thick, dark gray layers. This is the universally useful frozen base model. It contains the base language understanding, syntax, logic, and general reasoning that the model spent billions of compute hours developing. It handles frozen parameters in the range of 32 to 350 billion, depending on the model. At the top in orange sits the task-specific trainable layer. This is where we inject the highly specialized enterprise behavior we need. The trainable parameters here are a fraction of the total, between 6 million and 1 billion, as shown in the label at the bottom right. And that's the entire insight. Pre-trained foundation models already understand language. Fine-tuning simply swaps out or adds a final layer to dictate highly specialized enterprise behavior. Think about what this means in practice. We're not rewriting the athlete's muscle memory, neural pathways, or years of physical conditioning. We're handing them a new playbook, a very specific set of rules for our court, our team, our game. The frozen layers protect the general intelligence we paid billions of compute hours to build. The trainable orange layer is where we make our investment. And because it's so much smaller, that investment is dramatically cheaper, faster, and more targeted. This architecture is the foundation of everything we'll discuss for the rest of this session.
Before we get to the efficient solutions, we need to understand the problem they were designed to solve. This slide calls it the brute force era, full fine-tuning, and the numbers make clear why it earned that name. Full fine-tuning means exactly what it sounds like. You take a pre-trained model and you update every single one of its billions of parameters simultaneously. There is no freezing, no shortcuts. You are rewriting the entire brain. Look at the terminal output on the right. To do this with a 75 billion parameter model like GPT-3, you need to store 3 separate massive data structures simultaneously. 700 gigabytes for the model weights, another 700 gigabytes for the gradients, and another 700 gigabytes for the activations. Add it up, and you arrive at that number dominating the screen, 2.1 terabytes. That is your memory wall. To put that in human terms, a high-end consumer GPU today has around 24 gigabytes of VRAM. You would need roughly 90 of them working in concert just to hold the data before doing any actual work. The orange callout on the left makes the business consequence explicit. Updating all parameters creates a 2.1 terabyte memory wall, requiring millions of dollars in specialized, clustered hardware. And there's a second, more insidious problem the slide doesn't fully show: catastrophic forgetting. When you retrain the entire model on your narrow dataset, the model becomes so focused on your specific domain that it begins to degrade at general language tasks. You've over-specialized your athlete to the point where they've forgotten how to run. Full fine-tuning is powerful, but for most enterprises, it's simply not a viable option.
The memory crisis of full fine-tuning led researchers to a clever architectural workaround: adapter-based fine-tuning. This slide frames it clearly as a trade-off, with a win and a penalty that are both significant. Here's the architecture. The massive frozen base model, 175 billion parameters, sits at the top. Data flows down from it. But before the inference output exits, it passes through a small bottleneck, the adapter layer, shown in orange at just 1.75 billion parameters. That's roughly 1% of the base model size. The win is real and substantial. By freezing the base model and only training the adapter, we reduce trainable parameters to 1 to 10% of the full model. The memory requirements drop dramatically. The general intelligence of the base model is preserved, no catastrophic forgetting. But look at the penalty and read it carefully. Forcing sequential data through new layers introduces permanent inference latency for every single user request. This is the hidden tax. The adapter sits in the middle of the data flow. Every time a user sends a prompt, the data must pass through that bottleneck adapter before producing an output. This adds measurable milliseconds to every response. At scale, across thousands of concurrent users, those milliseconds compound into a serious production performance problem. The summary at the bottom is the key design lesson. Adapters solve the memory crisis, but penalize production speed. Adapters were a significant step forward, but the enterprise world needed a solution that captured the memory savings without paying the inference latency tax. That solution is what we cover next.
This slide introduces what is arguably the most important algorithmic breakthrough in practical enterprise AI over the last 3 years: LoRA, low-rank adaptation. Look at the left-hand diagram first. Notice the key difference from adapters. The LoRA module doesn't sit in the sequential data path. Instead, it runs in parallel to the frozen base model. The data flows through the original model on one path and simultaneously through the compact LoRA module on a separate path. Their outputs are then summed. This is what enables zero inference latency, and it's the fundamental architectural breakthrough. Now look at the right side, where the math becomes very concrete. A standard weight matrix in a large language model might be 768 by 768. That's 589,000 parameters. LoRA doesn't update that massive matrix directly. Instead, it decomposes the update into two much smaller matrices, a tall, thin matrix A and a short, wide matrix B, and trains only those. The result of multiplying A and B represents the weight update, but uses only about 6,000 parameters. The formula at the bottom captures this elegantly. Y equals W0 times X plus A times B times X. The original model output plus the low rank update. During inference, you simply merge the two together, and suddenly there is no bottleneck, no extra layer, no latency penalty. The result? A 100 times reduction in trainable parameters with zero speed penalty at inference time, and research consistently showing 99% of full fine-tuning performance. LoRa doesn't compromise quality for efficiency. It achieves both simultaneously. This is why LoRa has become the default choice for enterprise AI customization.
LoRa solved the trainable parameter problem, but there was still one remaining obstacle: the base model itself. Even if you only train a small LoRa module, you still have to load that enormous frozen base model into memory, and in its native 32-bit floating point format, that's still hundreds of gigabytes. This slide shows the solution: quantization, and the visual makes it immediately intuitive. At the top, you see the 32-bit float representation, a wide continuous bar, extremely precise, but massive in terms of memory. These are the raw, uncompressed model weights. Then the arrows push them through a compression filter, and what comes out the bottom is a 4-bit integer representation, segmented blocks, smaller, chunkier. The caption underneath tells you everything. Retains the general shape, tiny memory footprint. Here's the key insight. A model's weights don't need to be perfectly precise for inference to work well. The vast majority of a model's intelligence is captured in the relative magnitudes and relationships between its parameters, not the exact floating point precision of each individual weight. Quantization exploits this. It sacrifices microscopic precision to achieve a massive reduction in baseline memory footprint. Going from 32-bit float to 4-bit integer compresses the model to roughly 1/8 its original size in memory. A 70 billion parameter model that would require 280 gigabytes in 32-bit format now fits in roughly 35 gigabytes in 4-bit. And critically, as we're about to see, when you combine 4-bit quantization of the frozen base model with LoRa adapters trained at higher precision on top, you get something extraordinary: QLoRA.
This slide is where the economics become undeniable. This is the QLoRA advantage, and the numbers speak for themselves. Look at the comparison. Full fine-tuning of a large model, 2.1 terabytes of RAM required. That's the number we established earlier, the memory wall that requires millions in specialized hardware. Now, look at QLoRA. The total memory requirement drops to just 88 gigabytes. Let's break down where that number comes from, because the slide shows it explicitly. 87.5 gigabytes for the 4-bit quantized base model, plus just 1.3 gigabytes for the LoRa adapters running on top. That's a 24 times reduction in required RAM. Not a small improvement, a fundamental change in what hardware is even required. This is what the slide title captures: QLoRA, maximum leverage, minimum footprint. The description below the title says it plainly: the ability to fine-tune state-of-the-art models on consumer-grade hardware. Think about what that means operationally. You are no longer planning a multi-month capital expenditure for a specialized GPU cluster. You are purchasing or renting a single high-end workstation GPU, an RTX 6000, for example, and running the fine-tuning job in days, not weeks. The enterprise implication is profound. QLoRA transforms custom AI development from a capital expenditure that requires board approval into an operational experiment that a data science team can run and iterate on rapidly. This is the inflection point where custom AI became accessible to enterprises that are not Google or Meta.
The second major pillar of unsupervised learning is dimensionality reduction, and the visual on this slide is one of the most clarifying images in all of machine learning pedagogy. Look at the top half, a dense, tangled three-dimensional hypercube, hundreds of nodes connected by a web of lines in every direction. This represents your raw feature space, perhaps 500 columns in a customer data set, all interacting in complex ways that are impossible for a human to visualize or interpret. It's information overload. Then look at the bottom half, those same data points, flattened onto a clean two-dimensional grid, beautifully separated into three distinct color clusters, red, yellow, and green. The noise is stripped away. The signal is preserved. The structure that was invisible in 500 dimensions is now immediately obvious. That transformation is what dimensionality reduction does. The goal, as stated on this slide, strip away noise and compress features while preserving the most important mathematical information. The technique used here is principal component analysis, or PCA. Think of it as a high-powered executive summarizer for your data. PCA identifies the directions in your feature space that explain the most variance, the principal components, and projects everything onto those axes. The benefit is threefold. It reduces computational cost, it prevents overfitting by eliminating noise, and it makes high-dimensional data visualizable by humans. Enterprise applications include image compression, facial recognition speed optimization, and gene expression analysis in biomedical research. PCA doesn't just save compute, it reveals the hidden geometry of your data.
Let's make this concrete with a real-world scenario. This slide presents the enterprise ROI diagnostic, fine-tuning a Llama 2 70 billion parameter model for enterprise customer service. Same model, same task, same data. Two different approaches. On the left, full fine-tuning. Hardware need an 8 GPU cluster of NVIDIA H100s, the most powerful data center GPUs available at roughly $10,000 each. Training time, 7 days of continuous computation. Cloud compute cost over $50,000, and that's just for one training run. If your results aren't satisfactory and you need to adjust hyperparameters and retrain, that's another $50,000 and another week. On the right, QLoRA. Hardware need, a single RTX 6000 GPU, a high-end professional workstation GPU. Training time, 1 day. Cloud compute cost, approximately $500. Read that comparison again. Same 70 billion parameter model, same goal. $50,000 in 7 days versus $500 and 1 day. The bottom banner states the business transformation precisely. Parameter-efficient fine-tuning shifts custom AI from a capital expenditure to an operational experiment. This is not a marginal improvement in efficiency. This is a complete restructuring of the economics of custom AI. With QLoRA, your team can run 10 experiments, testing different datasets, different hyperparameters, different training strategies, for the cost of a single full fine-tuning run. The speed of iteration alone is a competitive advantage. Any executive evaluating a custom AI initiative today should have this slide in front of them.
We end this session with the most important summary slide in Module 2, and one that I want you to internalize deeply. This is the Pareto optimization of AI. The visual is a seesaw. The enormous gray block represents the massive weight of traditional full fine-tuning, the capital cost, the hardware requirements, the time investment, and it's balanced against a single orange triangle pivot point, parameter-efficient fine-tuning. 3 numbers define the breakthrough: less than 1% of the trainable parameters, approximately 1% of the hardware cost, and 99% of the task performance. Read that ratio clearly. You are deploying less than 1% of the computational effort and less than 1% of the financial cost, and capturing 99% of the result. The text at the bottom states the enterprise thesis explicitly. In enterprise AI, you don't need to rebuild the athlete. Parameter-efficient fine-tuning allows you to deploy massive, world-class intelligence and teach it your specific playbook for pennies on the dollar. This is the economic unlock that has changed enterprise AI from 2023 to today. It's what allows a mid-sized enterprise with a modest data science team to compete with organizations that have orders of magnitude more resources. Now, there's one important caveat. Fine-tuning, even QLoRA, is about changing a model's behavior and personality. It teaches the model how to be a doctor, a legal analyst, a customer service agent. But what if that model needs to answer questions from a 500-page manual it's never been trained on? For live dynamic knowledge access, we need a completely different architecture. That's what we'll cover in session 2.3, Retrieval Augmented Generation. I'll see you there.